Thanks for the organizers and everyone being here today. My name is Junya, Zhou, and I'm glad to present my joint work with Collin Raymond from Cornell University on complexity, communication, and misrepresentation.
You may have to use the keyboard.
Oh, the keyboard? It's not working.
You should use the mouse. The mouse works.
Okay, thank you. Okay, so the motivation is in a lot of real-world situations, communication is often complex, and individuals need to communicate related details. For example, in a murder investigation, the police officer won't just ask directly, "Did you murder this person?" Instead, he will ask related details in the alibi. Like, for example, where were you at 8 p.m. last night? Who were you with? So ex post conditioning on the police officer already knows whether the suspect committed the crime or not, the additional questions are similarly redundant or payoff irrelevant. But it is useful to ask these additional details because it makes it more difficult for the suspect to tell a consistent story if he is lying. And it is difficult because individuals have bonded cognition, like limited memory, to keep track of lies. So complex communication does not only happen in interrogations, but also other social interactions. So for example, when we file an insurance claim, we need to provide details of the accident. Or like if Mary wants to find out her husband's whereabouts last night, she can also check additional details. So this contrasts with the traditional approaches we typically use in economics, like where we have agents report minimal information, like the payoff relevant state or your true type. So previous literature kind of misses out all the potential of asking this similarly redundant information to get more information transmission. So in this paper, we try to study the impact of bonded cognition on complex communication. And we show the differential impact on the cognitive burden of constructing a truth versus a lie. And we also show the differential impact on the sender and receiver. So in this paper, we try to pin down conditions where making reports convey redundant information generates new and more informative equilibria in complex environments. So this result is particularly interesting because like in standard assumptions of cheap talk, there's only a Balaban equilibrium and there should be no change in equilibrium. But with complexity and bonded cognition, we can achieve a new and more informative equilibrium. So the approach we use has three novel features. So the first is that players need to report information that is redundant and players have bonded cognition. We're going to use the example of limited memory. It's just because it is easy to implement in the lab. And we also change the complexity of the environment. And so the features generate two key intuitions. So the first is that players must exert costly efforts to construct a convincing lie. And complexity increases the relative cost of consistent lying compared to truth-telling. And we then develop a stylized model that captures the intuitions. And we also run a large lab experiment with almost 700 subjects to test the theoretical predictions. And we also work on multiple extensions. So here's a list of related literature. So I will just go straight to the basic setup. So the basic setup is very similar to a standard cheap talk game. We have two subjects, a sender and a receiver. So there are three states of the world, up, middle, and down. So the sender observes the realized state and sends a message. And the receiver doesn't observe the realized state and only sees the sender's message. And then the receiver chooses an action, up, middle, and down. And sender and the receiver have misaligned preferences. So the sender always wants the receiver to choose the up action, but the receiver wants to correctly match the state. So this is the payoff matrix we use for the lab experiment, but our theory is more general and is not restricted to the specific numbers. So from this matrix, we can see the sender gets the highest payoff if the receiver guesses up, the second highest payoff if the receiver guesses middle, and the lowest payoff if the receiver guesses down. But the receiver gets the highest payoff for correctly matching the state. So if the state is up, the sender is happy to tell the truth, but with the middle and down states, the sender has the incentive to lie, and the receiver also knows that. So under standard assumptions, there's only a Balaban equilibrium in this environment. So like the receiver just ignores the sender's message and there's no information transmission. So next, I'm going to show how we enrich this typical environment to get a different and a more informative equilibrium. So now each state is associated with an additional attribute, and each attribute can take on one of k values. And the attributes do not influence payoffs directly, and the profile of attributes is different for each state. So I will go directly to the experiment, which captures the key intuitions and also has a brief touch on the theory. So consider two environments. So now we have a simple environment. Now each state, like up, middle, down, is associated with three attributes. So we have a background color, a center shape, and a letter. And we also have a complex environment where each state is associated with 4 cards, and each card has 5 attributes. So we have a background color, a letter, shape, number, and a mathematical symbol, and there's a total of 20 attributes. So in this environment, the sender needs to report the state up, middle, and down. This is similar to the standard sheet talk. What is different is now the sender also has to report a subset of the additional attributes. So in the simple environment, the sender needs to report all 3 attributes. And in the complex environment, the computer randomly selects 3 out of 20 attributes and asks the sender. So note that when we move from simple to complex, the sender's message contains the same amount of information. So like 1 message about the realized state and 3 additional messages about the associated attributes. So we're not changing complexity of actual communication. We're only like exerting more cognitive burden for the sender to construct a consistent lie. So I would like to walk you through the interface to explain the sequence of events. So in the first stage, both the sender and the receiver are given 15 seconds to look at the 3 states and the associated cards. So this is the stage where subjects can exert costly effort to try to memorize the associated attributes. And then in the second stage, only the sender observes the realized state and associated cards. And so in this example, set middle is realized. So the sender only observes the middle set of cards, and the sender cannot observe the up and down states of the set of cards anymore. And then the sender needs to answer the following 4 questions. So what's the draw setting this round? Like up, middle, or down? And then 3 randomly selected questions. So for example, like what's the sender letter of the second card? So if the sender is telling the truth, it's very straightforward. They can just read from the cards shown on the screen. But if the sender wants to lie, now he needs to recollect, oh, what's the sender letter of the second card? So can anyone in the audience still remember that? So this is the way like we try to exert this cognitive constraint on the sender side. And then the receiver sees the sender's responses and choose a guess. So like up, middle, or down. And then like subjects get feedback, like payoffs, like the message, guess decision, and also consistency of the message. So I would like to clarify some key concepts here. So in our environment, the sender can either lie or tell the truth. So we say a sender is lying if the reported state is not the realized state. For example, report up if the realized state is middle. And a lie can either be consistent or inconsistent. So we say a lie is consistent if all reported attributes match the reported state. And a lie is inconsistent if at least one of the reported attributes does not match the reported state. So for example, we can say like the state is associated with attributes 1 red square, and the middle state is associated with 4 blue triangle. So a consistent lie if the sender reports up and 1 red square. So all 3 attributes are correct. And an inconsistent lie is in the case, for example, the sender reports blue attribute instead. So this blue attribute is actually associated with the middle state, but not the up state. So this is an inconsistent lie. And we can have similar definitions on consistent and inconsistent truth. So this is a description of our main segments. So what we're doing here is very straightforward. So we're going to increase complexity of the environment by changing the total number of additional attributes. So we change the number from 3, which is a benchmark, like very easy to memorize, to 20, and then to 40 and 80. So kind of make it almost impossible. And on another dimension, we also try to make things easier for the receiver because they also need to memorize the attributes to detect inconsistency in the sender's message. So this is some logistics. What's important here is that we have random matching in every round, and subjects observe a new set of cards. So there's no repetition. And so we have 364 subjects for the main treatments, and we also run like several more. So next, I'm going to talk about the key experimental findings. So I'm going to talk about like how bounded cognition influences the sender and receiver with increasing complexity and how their interaction influences the communication outcome. So first, on the sender side, we can see with increasing complexity, there's a different impact when they tell the truth versus when they lie. So when they tell the truth, which is shown in the blue line, we can see there's no significant change. So recall, the sender always observes the realized state and associated attributes, so they don't need to memorize to tell the truth. So there's no change when we increase complexity. But in contrast, in the red line, when senders lie, now it is based on the memory. There's a significant decrease when we move from simple to complex. And it decreases further with 40 and 80 attributes. So first of all, like increasing complexity significantly reduces the sender's ability to construct a consistent lie. And on the receiver side, it's a little bit more implicit because we only observe the receiver's guess decision, but we don't know whether the receiver detects inconsistency in the sender's message or not. So we need a structural model where we assume noisy best response. So this figure shows the estimation results of the receiver's estimated detection rate of inconsistency in the sender's message. So we can see that with increasing complexity, it also impacts the receiver's ability to detect inconsistency. So the communication outcome is determined by their interaction on the sender side and the receiver side. So in this figure, we show the blue line is the sender's truth-telling rate. We can see when we move from simple to complex, there's a significant increase in sender's truth-telling rate. So because like now they see if they are going to lie, it is very possible that it is going to be inconsistent. So the sender decides to tell the truth to begin with. And with increasing complexity, the sender still tells the truth quite a lot. But surprisingly, we don't see a similar pattern on the receiver's guess. So there's actually a non-monotone relationship. So in simple, it is very easy for the sender to memorize the 3 attributes and tell a consistent lie. The receiver cannot detect inconsistency, so we have low information transmission. But with very high level of complexity, it is also very difficult for the receiver to detect any inconsistency, which also leads to low information transmission. So in the middle, with this medium level of complexity, it's difficult enough for the sender, but relatively easy for the receiver, we have like more information transmission. So there's a non-monotone relationship between complexity and information transmission. So to further explore this impact, we have 2 additional treatments where we give receiver additional assistance. So one is question assistance, tell receiver selected attributes in advance, and then we also have a detection assistant treatment, so where there's no memory difficulty on the receiver side. So we can see if we give receiver assistance, there's no non-monotonicity anymore, and we can see a significant increase in the receiver's guess decision. So we would make it difficult enough for the sender, but make it easy enough for the receiver. There's even more information transmission. So this is kind of as expected. So this figure is trying to do some statistical significance. So what we're doing here, on the x-axis, we have the relative complexity measured by the difference between the receiver's detection rate minus the sender's consistent lying rate. And then on the y-axis, we plot the correlation between the state and the receiver's guess. So this is a measure of information transmission. And we can see a statistically positive correlation. So the complex mechanism works best when it is difficult enough for the sender to tell a consistent lie, but relatively easy for the receiver to detect a lie. So I don't have time to talk all about this, but in the paper, we have a model of bounded cognition that captures the intuitions. And you can think of it as a rationing attention model where the sender has difficulty understanding the association of the state and the additional attributes. And we also run several additional treatments, like where we make it also difficult to tell the truth and test for alternative mechanisms. We also elicit like subjects' preferences for complexity and also like standard sheep talk as a robustness check, etc. And we also have some heterogeneity analysis where we show like memory and cognitive reflection ability influences information transmission, but through distinct channels. We also have some like level K analysis as well. So a short summary, I would like to highlight our key contributions. So first, we extend theory and empirics of strategic communication by developing a behavioral model with bounded cognition. So we show eliciting payoff irrelevant information leads to new and more informative equilibrium. And we construct a framework integrating complexity for both sides. So it is a race between the sender's ability to tell a consistent lie and the receiver's ability to detect a consistent lie, detect a lie. So more broadly, I see our results help explain like why we see so many complex communication in real life situations. And it also points out to the way economists and mechanism designers can leverage in situations where individuals do have bounded cognition. So that's all for my presentation. I'm ready to take any questions or comments. Thank you.